In the previous video, we saw how to use separation of variables in order to solve a first-order differential equation like this, and we came up with a solution that was like this. In general, the types of problems and differential equations that we'll be trying to solve will be more complicated than that, and so we won't be able to use separation of variables. So we'll be using, namely, our Laplace Transform techniques, but it's also worth understanding how to check that a solution is actually a solution. So that's what we're going to do here. So even though we already know the solution from the previous slide, what we're going to do is we're going to show that this is indeed a solution to this differential equation. So that's your first step. So that really is just about plugging in what y dot is and what y is and proving that that equals 0. The next thing is you're going to use Laplace Transform to find the solution. So go through the whole process of finding the solution based on some initial condition, y of 0. And then what I'd like you to do is think through the different forms of the solution. So we know that the solution looks like this, but then the question is, what could the trajectory of y look like over time? So depending on the value of k, this exponential can look different, look like essentially different profiles. And so what I want you to do is think about those, and those characterize all the types of behaviors that a first-order differential equation can exhibit. And remember here, when you think about in this particular sequence for this particular class, we're going to be talking about homogeneous behavior, which means all the behavior that happens not due to inputs. And so the only thing that's causing motion or the trajectory of the system are these initial conditions. So you think about those initial conditions as being kind of quote-unquote inputs because they're what's driving the dynamics. So we don't have any sort of other inputs. So go ahead and press pause and attempt these three, and then I'll go through my solution. All right, so our first task is to verify that this is a solution to this differential equation. The way we do that is we just plug in. So we're going to plug in for y what we have for y. So we're going to plug that e to the minus kt in there. Then we want to know what y dot is, and remember y dot is just dy dt. So we're taking the time derivative, the t derivative of the function y. So if y looks like this, then when I take the derivative with respect to t, I'm going to take the derivative of this exponential. So t is the variable that with the derivatives with respect to. So that means that a factor of this minus kt gets pulled down in front. That's essentially the chain rule. And you get minus k times e to the minus kt. So that is the derivative of y with respect to t. And so now I can just take this and plug that in wherever I see y dot. So in this case, that becomes minus k times the exponential plus k times the exponential. And so if we factor the exponential out, because they're the same, you get minus k plus k. Those cancel out, and 0 multiplied by this exponential gives 0. And so what that is telling us is that when we substitute in this functional form into this differential equation, this first-order differential equation, we get 0. And so that is why it's a solution. It is a function that when you plug it in, it satisfies the equation. So that means that this y obeys the rule that is specified by that differential equation. So using the tools that we've been building for Laplace Transform, we're going to take the Laplace Transform now. This is the second part of the activity. So that y dot, we get s times the Laplace Transform of y minus the initial condition. And then from here, you get k times the Laplace Transform of y. And so that's important to remember. Remember, when you take the Laplace Transform of y, you get capital Y of s. So remember, I'm leaving off the of s, so that capital Y is really a function of s. And the Laplace Transform of 0 is 0. And so when we solve for y in terms of everything else, we get y of 0, that's our initial condition, over s plus k. And so when we look that up in our lookup tables, this 1 over s plus k gives us this exponential, e to the minus kt. And so that's another way to get this same functional form that we got here using the Laplace Transform. And then what you'll notice is that the initial condition is just falls just like that. And that makes sense because when you plug in t is equal to 0, e to the minus k0 is just 1. And so then y of 0 is literally y of 0. All right, now in the third part of the activity, you're going to draw the different kinds of behaviors that you can see. So with a functional form that looks like e to the minus k times t, really the only thing that changes, so t is a variable that's going to go from 0 up to infinity, and so k is really the only thing that can shape the way that this behaves. And so what you'll notice is that if k is positive, you'll get this decreasing exponential. It's going to start out at essentially 1, or it could be y of 0 if you wanted to think about it that way. And it's just going to decrease over time because that exponential is negative, the exponent is negative. If k is negative, so in the case where k is negative, that means that the exponential exponent is positive, and so that means it's going to be a growing exponential, so it's going to grow exponentially. And then the other kind of in-between case, which is maybe it has to be exactly equal to 0. When k is exactly equal to 0, then this value just stays exactly the same over all time. And so we haven't really talked about this, but let's just start introducing some of these terminology. So this is stable because it's not blowing up. So this y value is decreasing over time. It's not trending off to infinity. Whereas this is unstable because over time, y increases and increases, or it could be decreasing, could be going negative, but it's going to infinity. This is kind of a limiting case, and sometimes in the middle here, we'll call this marginally stable because it's not diminishing down to 0, but it's not blowing up. And so this is a kind of in-between case, sometimes called marginally stable.